Answering a past paper question from paper 2, AQA A Level Chemistry. This question is about the rate equation and the rate determining step, one of the most common questions in paper 2. In this question, propanone reacts with bromine in alkaline conditions, and this is the equation for the reaction. And they give you the rate equation for the reaction. We notice from the rate that it's first order in terms of the ketone, and also first order in terms of the hydroxide. However, it's zero order in terms of the bromine. Now, the first question, they ask you to sketch a graph on the axis provided to show how at constant temperature the concentration of bromine changes during the reaction. Of course, the concentration of bromine will decrease. Normally, when we draw this, we draw it with a negative decreasing gradient like this. So this is how the graph is drawn. And then the second question is that they give you the three different experiments where they provide you with the initial concentration of all the three reactants and the initial rate. And they ask you to complete the table. This is a very common question in the exam. Will they give you a table and ask you to complete some of the concentration or of the initial rate? Here, and remember that when we saw the rate equation, that it's first order for the ketone and first order for the hydroxide, while it's zero order for the bromine. So bromine concentration will not affect anything here in the initial rate. So first of all, let's see the first one here. They want you to calculate the concentration of the hydroxide. The first column or the first experiment, the concentration of the ketone was provided and the concentration of the hydroxide was provided, and this is the initial rate. Now, in experiment number 2, you can see that the concentration of the ketone hasn't changed and the rate has changed. The rate has increased, and when you find the factor of the increase of the rate by dividing the new rate by the first one, you're going to find that it increased 3 times, meaning the concentration of the hydroxide, because it's first order, also increased 3 times. So you multiply the initial concentration from experiment 1 times 3, and that will give you the initial concentration for the second one. So it's going to be 7.50 times 10 to the minus 2. And then when we look at experiment 3, we're going to find that both the ketone and the hydroxide concentration have changed, and they want you to calculate the initial rate. Again, this is first order. When you see that the concentration of the ketone, you're going to find that it decreased 4 times, meaning you're going to multiply this by 0.25. And for the hydroxide, the concentration has increased compared to the first one, increased 4 times, which means we're going to multiply this by 4. So when you take the initial rate from the first one, multiply this by 4 and also by 0.25, that will give you the exact same initial rate, which is 2.75 times 10 to the minus 11. So this is the initial rate for this one. And then they ask you to use the data from experiment 1 to calculate the rate constant for this reaction. So we know that the rate equals the rate constant times the concentration of the ketone times the concentration of the hydroxide, which means the rate constant will equal the rate divided by the concentration of both reactants. So CH3, COCH3, and concentration of the hydroxide as well. Let's plot these values for the first experiment. So it's going to be 2.75 times 10 to the minus 11, and divide this by the concentration of the hydroxide, which is 2.5 times 10 to the minus 2 times the 1.50 times 10 to the minus 2. And then you can find the value of the K, or the rate constant, which is 7.33 times 10 to the minus 8. And now they want you to find the units. So let's have a look. The initial rate unit is mole decimeter minus 3 second minus 1. and then the concentration of both reactants because it's first order. So this is mole decimeter minus 3, mole decimeter minus 3. So now let's simplify this one. So you're going to find that the units are mole minus 1, decimeter cube, and second minus 1. So these are the units. Then the following question, because this is kind of organic reaction, they want you to complete the mechanism of the reaction. Look at the number of marks for this reaction. It's 4 marks for this question. It's 4 marks, meaning there are 4 different curly arrow that you will have to draw because each arrow will be 1 mark. So let's have a look at step 1. In step 1, we have the hydroxide attacking as a base, attacking this hydrogen and taking it as a proton. And when we look at the product, you're going to find that the oxygen now has a negative charge and there is a double bond between the 2 carbons. To generate the double bond between the 2 carbons, that means these electrons will have to move from the carbon hydrogen towards the carbon carbon. And for the oxygen to have the negative charge, that means that the double bond will have to move from the carbon oxygen towards the oxygen. So these are 2 curly arrows. And step 2, you're going to find that the bromine was going to be attacked by the double bond between the 2 carbons. Now let's have a look at the final product. And the final product, bromine has been introduced, and then again we regained the double bond between the carbon and oxygen. To regain the double bond, first you will need to have a lone pair of electrons here on the oxygen, and then it has to move to give you the double bond between the oxygen and the carbon. And also don't forget, because bromine has been added, now this bond between the 2 bromide has to break as well. So now we have added 4 different arrows, and these are all the arrows that are required for to complete the mechanism. And finally, they ask you to use the evidence from the equation, the rate equation, to explain why step 1 is the rate determining step. Remember that the rate determining step is always that step that has all the species that we can find in the rate equation. So now step 1 has these 2 species, the OH and the ketones, and these 2 are in the rate equation. So the evidence here that step 1 includes all species which are the ketones. You can either name the species and write the ketone and the hydroxide ion, which are in the all the species in the rate equation. So this is how to answer this question. Let's answer this past paper question from paper 2, AQA A Level Chemistry. This question is about equilibrium. The equilibrium reaction is 2P plus 1 of the Q will give you 1 mole of R and 3 moles of S. Let's have a look at the information they give us in this question. So they say that 25 centimeter cubed of a sample of a solution P is added to 20 centimeter cubes of a sample of a solution Q. That means the total volume of the solution then of the reaction will be 0.045 decimeter cubed or 45 centimeter cubed. And also they give you the amount in the equilibrium mixture for all of the reactant and products, the amount in moles. The first question asking you to calculate the amount in moles of P before the reaction with Q. Then to calculate the amount of P, you need to know exactly how many moles of P reacted. When you look at the balanced equation, you're going to find that 2 moles of P will get you 1 mole of R. That means that the moles of P reacted will be double the moles of R that were produced. So the total amount of the P, so the total moles of P before the reaction will equal the moles remaining of P at equilibrium, which are 0.0145 moles, plus double the moles of R, so 2 times 0.0115 moles, and that total will be 0.0375 moles. And then they ask you to use this answer to calculate the concentration in mole per decimeter cubed of P in the initial 25 centimeter cubed of the sample. Of course, the concentration equals the number of moles over the volume in decimeter cubed, so 0.0375 divided by the volume in decimeter cubed, which is 0.025, and that will give you the concentration, which is 1.5 mole decimeter per decimeter cubed. So amount of P 0.0375 and concentration 1.5 mole per decimeter cubed. The next question asks you to give the expression of the equilibrium constant, Kc, and calculate the value of Kc and deduce its units. Of course, we know that the equilibrium constant will equal the concentration of the products, each raised to the power of its moles, divided by the concentration of the reactants raised to the power of their moles. So going back to the balanced equation, we're going to find that there are 1 mole of R, 3 moles of S as product. So it's going to be concentration of R times the concentration of S cubed. And then when we look at the reactants, we have 2 moles of P and 1 mole of Q. So this is going to be P squared multiplied by the concentration of Q. Now we need to find the concentration, and the concentration here is going to be the moles of each of these at equilibrium divided by the total volume of the solution. We calculate the total volume as 45 centimeter cubed, and we should calculate that in decimeter cubed, which is 0.045. So now we need to add the different concentrations of each of these. So let's start with the product. So the R equals 0.0115 divided by the volume, 0.045. And then for the S, it's 0.0345 moles divided by 0.045. Don't forget to put the cube. And then the concentration of P at equilibrium, the number of moles is 0.0145 divided again by 0.045. And this is squared because there are 2 moles of P. And finally, the Q, the remaining or the number of moles at equilibrium is 0.0275 divided by 0.045. And when you do your calculation, you're going to find that the value of Kc is 1.817. So you can say it's almost 1.82. Now we need to find the units. Remember that we can find the units based on what are the different terms for the concentrations we've used and the powers we have used. So let's simplify this or take it step by step. So for the R, it's going to be mole over decimeter cubed. And then that's multiplied by the cubed of the concentration of S. So it's going to be mole cubed over decimeter to the power of 9. And then that's going to be divided by the P squared. So it's mole squared over decimeter to the 6. And then for the cube, it's mole over decimeter cubed. So these can be simplified together. And then you're going to find that there are cubed here at the top, and at the bottom there is the it's cubed and over the the mole squared over decimeter to the 6. So the final unit will be mole decimeter minus 3. So the units here are mole decimeter minus 3. And the final question asks you to explain why the amount of S, which is one of the products, will increase when water is added to the equilibrium mixture. So when the water is added to the equilibrium mixture, the concentration of all of the reactants and products will decrease. And so the equilibrium will shift to the side which has higher number of moles. When you look at the reaction, you're going to find there are 3 moles on for the reactants, and there are in total 4 moles for the products. So equilibrium will shift towards the products, which mean the concentration of the or the amount of S and also for the R will increase. So the equilibrium will shift or shift to the side with the most moles, which mean towards the products, which is the S and R. And this is to oppose the decrease in the concentration of all reactants and products. Remember also that you can also say that the Kc is expressed as a function of concentration, and the concentration of equals the amount in moles over the volume. And when the volume increases, the amount of the moles have to increase in order to keep the Kc constant, which means that the amount of the moles of the S and R will increase. So either of these will be accepted as your answer. Let's answer this past paper question from paper 2, AQA A Level Chemistry. I posted this question yesterday and asked you to try to answer it before I post the answers. And this video is to walk through this question and answer the different questions to give you the proper exam techniques. So this is about hydrocarbons and about catalytic cracking. The first question, they get you C20H42 as hydrocarbon, which has been cracked by heating to 700 K in the presence of a catalyst. The products are an aromatic hydrocarbon, an alkane C6H4 for C6H14, and another alkane. They give you the equation and they want you to complete the equation for the reaction. So this is the aromatic one, C8H10, and this is the first alkane, C6H14. So when you add the different carbons and hydrogens of the products and take that away from the total carbon and hydrogens of the reactant, you're going to find that the remaining carbons and hydrogens are C6H18, which means that we cannot have a single hydrocarbon there because C6 will never have 18 hydrogen. So if it's C6 hydrocarbon, it will mean that we'll have 14 hydrogens. So it's not that one definitely, and it's already one of the product. It's a different hydrocarbon, so it must be a smaller one. So let's start with the simplest one we can find, which is the methane, CH4. And if we have CH4, that means we're going to have 6 of the CH4 to have 6 carbons, but then the total number of hydrogen will be 24, so it cannot be the methane. And then moving on to the ethane, which is C2H6, and we need to have 3 of these. So when you have 3 of the ethane, you're going to have 6 carbons and 18 hydrogens. So this is the correct answer. So 3 C2H6. Now they ask you to give a suitable catalyst for this reaction. There are 3 different catalysts that you need to know, but here you only need to mention one of them. So I'm just going to write one of them, which is zeolite. So zeolite is one of these catalysts which are used for catalytic cracking. And then they give you the carbon-13 NMR spectrum of the aromatic hydrocarbon, which is C8H10. C8H10, that means if it's aromatic, that means we have a benzene ring, and then we have either 2 methyl groups or we could have an ethyl group. So let's have a look at the carbon-13 NMR. So in the carbon-13 NMR, we have 4 aromatic carbons, 4 different aromatic carbons, and we have only one aliphatic carbon, which means we cannot have an ethyl group. We can have 2 methyl group, which are chemically equivalent. So let's have a look at the different choices we have. So from A to D, you can find that D has an ethyl group, which is impossible. So this cannot be. Well, so all of the other ones, A, B, C, have 2 methyl groups, which are chemically equivalent, will give you only one peak for the aliphatic carbons. And then let's count the number of aromatic carbons for each of these. The one that will have 4 is the right answer. So the first one, we're going to have 1, and then all the other carbons will be chemically equivalent. So we're only going to have 2 signals. For the second one, B, we're going to have this is 1, and then this is 2, and then that is 3. These two are 3 chemically equivalent, and this is 4. So this one has 4 different carbons, aromatic carbons. So this is the correct answer. Question 3, asking you about the cracking can also be done without a catalyst, which is the thermal cracking, and using a temperature of 1200 K and a pressure of 7000 kilopascal. So state the type of the product. So we know that the thermal cracking ends up with the formation mainly of alkenes, unlike the catalytic cracking, which gives you aromatic hydrocarbons and smaller alkanes. So the main product here is going to be alkenes. Then this is a calculation question. So a sample of butane has a volume of 20 centimeter cubes at room temperature and pressure. The sample is burned completely in 1,350 centimeter cube of air. The final mixture is cooled to room temperature and pressure. And this is the equation. Because it has been cooled to room temperature and pressure, the water here is going to be just liquid. So all what we need to calculate for the gases will be the carbon dioxide and oxygen here. So they want you to calculate the total volume of gases in the final mixture. So first of all, we need to find out the volume of oxygen that actually reacted. So volume of oxygen consumed, in the reaction. From the balanced equation, we're going to find that 6.5 or 6.5 moles of oxygen will be used to burn 1 mole of the butane, which means that the 20 centimeter cubes of the butane will need the 6.5 times that of oxygen. So 6 times 6.5 will give you 130 centimeter cubed. So this is the volume of the oxygen consumed. And then the volume of carbon dioxide that is produced will be 4 times the volume of the butane that was burned. So 20 times 4, because there are 4 moles of carbon dioxide, which means 80 centimeter cube. Remember that the oxygen came from air and the total volume of air was 1,350. So the remaining volume of air at the end, remaining volume of air will equal the 1,350 minus the 1,130 centimeter cubed of oxygen that was used in the reaction. So that will give you 1,220 centimeter cubed. And finally, the total volume of the gases, at the end will equal the remaining volume of air plus the volume of carbon dioxide produced, which is 1,220 plus the 80 centimeter cubed. So it's 1,300 centimeter cubed. They give you here a bit of information that assume that the air contains 21% by volume of oxygen. You're not going to use this one. You could use it, but you're going to add extra steps in your calculation, and you actually don't need to use it. So just ignore this piece of information. And the final question asks you about the environmental problem of the formation of sulfur dioxide. So we know that sulfur dioxide is the main cause for the acid rain. So I would put the environmental problem as just acid rain, even though they would accept what acid rain causes or what are the problems of acid rain, like it damages limestone buildings or statues, or it causes death of aquatic organisms. But personally, I would just put acid rain. All of these will be accepted. And then they ask you about the formula of the compound that is used to help remove sulfur dioxide from the combustion product. So we know that the alkaline slurry is used, which is either calcium oxide or calcium carbonate. You can just write one of these two. You don't have to write both of them. You can just write calcium oxide or calcium carbonate. Let's answer a past paper question from AQA A Level Chemistry. This is paper 2 question, and this is organic chemistry question. They ask you about different isomers, all have the same molecular formula, and they give you some information about their analytical data. and ask you to deduce the structure of each isomer. So there are four compounds, V, W, X, and Y. They are all isomers with the same molecular formula, C5H10O2. Isomers V and W are carboxylic acid, so this is the first information, and they can be written as C4H9COOH. First of all, isomer V. So the information here is that isomer V has a symmetric carbon atom. We know that isomer V is a carboxylic acid, and we know that it has a symmetric carbon atom. A symmetric carbon atom means we have a chiral carbon. So to deduce the structure, first let's draw or write the carboxylic acid group, so COOH. And then it must have a carbon here. This carbon must be the asymmetric carbon. So what's remaining here? We can have a methyl group here, CH3, and then we can have an ethyl group on that side, CH2CH3, and then we could have a hydrogen here. So this is the asymmetric carbon, and this has the C4H9COOH. So this is isomer V. And then isomer W, which is also a carboxylic acid, it has four peaks in its proton NMR spectrum. So let's first deduce the structure of the W. So again, let's draw the COOH, and then let's think about the four peaks. So this is the first peak for the carboxylic acid hydrogen. There are remaining three other peaks. And in order to have three other peaks, we need to have two methyl groups here with six protons having the same peak. So we could have a CH2 here, and then we could have a carbon with two methyl groups, as you can see here, and then a hydrogen. So now this is one, and these two hydrogens are the second signal, and then these two CH3s are one signal, and then the proton here is the fourth signal. And then they want you to give the integration ratio for the four signals. You can put them in any order. So it can be 1, 2, 6, 2, 2, 2, 1. And then we have isomer X. Isomer X now is not a carboxylic acid. And remember again that the molecular formula is C5H10O2. And they tell you that it has three singlets with integration ratio of 1 to 3 to 6 in its proton NMR. And they want you to deduce the structure of X and explain why the peaks in the proton NMR spectrum are singlets. Then now let's think about the structure. First of all, there are six protons which are going to have the same signal, which means we have two methyl groups attached to a carbon, and this carbon cannot be attached to any hydrogen. So the only possibility, it can be attached to one oxygen on one side and one carbonyl group on the other side. This can be an OH, which is the singlet here for one proton, and then we have three protons, which are going to give us another signal, which is this CH3. As we can see, none of these protons have on the adjacent carbon. There's no hydrogen on the adjacent carbon. This is why all of these signals are singlet and they are not split. And finally, we have the isomer Y, again, isomer Y, C5H10, H10O2. And then this is the information about the peaks in their proton NMR. First of all, we have only two peaks and the integration ratio is 2 to 3. We know that the total number of protons is 10, which means that the number of protons here is actually 4 to 6. Let's have a look at the chemical shift. The chemical shift for the four protons here is 3.65, which means there are two CH2 groups which are each attached to an oxygen, because CH 3.65 means CH next to an oxygen. So what part of the structure will be responsible for this peak, which is 3.65? This is a singlet as well, so they must be chemically equivalent. So we can have CH2 and CH2, each of these attached to an oxygen. And then we have the part of the structure which is going to give us a peak at 119. So 119 means there is a CH next to a carbon. And now there are 6 proton, which means we're going to have 2CH3 groups. So the part of the structure can be CH3 and CH3. Both of these attached to a carbon, which is not attached to any hydrogen because it's a singlet as well. Now, the structure of Y, when we combine all of these, we're going to find that the only way to have this structure is to have carbon and then this carbon attached to the 2 oxygens and then the CH2 and the CH2, and then we have here the CH3 and CH3. So this could be the final structure based on what we have deduced from the peaks and their integration. And finally, they ask you the number of peaks in the carbon-13 NMR spectrum. So these 2 CH3s will give you 1 peak, so this is 1, and this carbon here will give you the second one, so this is 2, and then these CH2s, these 2 carbons will give you also one signal, so there will be 3. So the total number of carbon-13 NMR spectrum will be 3 peaks. Let's answer this past paper question from paper 2, AQA A Level Chemistry. And this question, they give you compound L with its molecular mass, which is 88. And in this question, they give you a certain number of moles of sample L was burned completely in air to form a certain number of moles of water and certain number of moles of carbon dioxide. This compound contains carbon, hydrogen, and oxygen. Remember that if we assume that this compound is carbon N, a number of carbons is N, and the hydrogens are M and oxygen, let's say X, and when it burns completely in oxygen or in air, that will give us N moles of carbon dioxide and M over 2 moles of water. That means for the balanced equation, for 1 mole of this compound, N and moles of carbon dioxide will be produced, and that will be the same number of carbon atoms. And the number of moles of the hydrogen, the water, the ratio between the moles of the compound and the water molecule produced will be half the number of hydrogen atoms, basically. So now we know the moles of how many moles of the carbon dioxide were produced. And if we divide the moles of carbon dioxide produced over the moles of the compound reacted, that will give us this ratio. So the number of carbon atoms will come from, or N will equal the moles of carbon dioxide produced, which is 2.62 times 10 to the minus 3, divided by the moles of the compound that reacted, which is 6.56 times 10 to the minus 4. That will give us 4. That means there are 4 moles of carbon dioxide for each mole of the compound reacted, which means there are 4 carbon atoms. And then M over 2, or the number of the water molecules, moles, or the ratio between the water molecules produced to for each of 1 mole of the compound reacted will also be given from the moles produced of water divided by the moles of the compound reacted or burned. Again, this is 4, which means M will equal 8 because M over 2 is 4. So now we know that carbon, there will be 4 carbons and there will be 8 hydrogens. Now we need to find the number of oxygen atoms in the molecules. The molecular mass of the molecules is 88, which means the remaining part, which is the oxygen, will come from 88 minus the mass of the hydrogens, which is 4 times the 12, and minus the 8 times 1, which comes from the hydrogen, which means the remaining here is 32. So 32 is the total mass of the oxygen in that molecule. We know that the atomic mass of oxygen is 16, which means that there are 2 oxygens here, because 32 over 16 will give us 2. So now the final molecular formula of the compound will be C4H8 and O2. Let's answer this question from paper 2, AQA A Level Chemistry. And this question is about amines. So the first question, there is an incomplete equation for step 1 in the reaction between bromoethane and an amine, which is shown below here. So they want you to complete the equation. Let's look at this equation first. So we have this alkyl halide, which has a bromide here, and there is an electrophilic substitution reaction. And when you look at the product, what is the part that has been added? It's this part. This part substituted the bromide. This is the first step in the nucleophilic substitution reaction. And you can see that a methylamine was added. So here this reaction is between methylamine, so NHH, and then CHH and H. This is the methylamine. And then they want you to name the secondary amine that will be formed in step 2 of this reaction. In step 2, there will be a base, which is another molecule of the methylamine, which is going to take the hydrogen from the nitrogen as a proton, and that will end up with the formation of the secondary amine. The amine that will be formed can be named in so many different ways, which one of them is, you can say, N-methyl ethylamine. So N-methyl ethylamine. You can also call it methyl ethylamine straight away, or you could call it methyl ethane amine. So whatever you're going to name it, it's correct and will be accepted. And then the second question, they give you another alkyl halide, which is 2-bromo butane. This is the one which reacts with ammonia. And then they want you to draw the skeletal formula of the major organic product formed under two different cases. The first one in presence of an excess of ammonia, and the other one in an excess of the alkyl halide. So first of all, when we use excess of the ammonia, the reaction will stop at the first step, which is the formation of the primary amine, a nucleophilic substitution reaction where the bromide leaves and it's substituted with an NH2 group or an amino group. So let's draw this one. So first of all, let's draw the butyl. So 1, 2, 3, 4 carbons. And then carbon number 2, which has the bromide group here, this is going to be substituted with an amino group. So NH2 here. So this is in presence of excess of ammonia. When you use excess of the alkyl halide, the reaction will continue. So the primary amine that is formed will again act as a nucleophile to attack the alkyl halides and do another substitution and so on. And the final product as a major product is going to be the quaternary amine. So now to draw the quaternary amine, you need to start with the nitrogen, and then you put the four substituents. Remember, it's going to be 2 butyl. So the 2 butyl, so you have one methyl group and one ethyl group on the other side. So you're going to continue like this, one methyl, one ethyl, and then another one methyl, one ethyl, and then one methyl, one ethyl. So in each of these, 4 carbons and the substitution at carbon number 2 of the butyl group. And then don't forget the positive charge on the nitrogen because it's going to be a quaternary amine group, quaternary amine that is formed. And of course, it's going to be a salt, so there will be bromide with a negative charge as well. Question 3, figure 3 here, as you can see, is a two-step tensors to make amine G. And they want you to complete figure 3 by drawing the mechanism for step 1 and the displayed formula of the amine G. So let's look at the product of step 1. The product of step 1, you're going to find here there is a bromide and there is a cyano group in the product, which means this was a nucleophilic substitution reaction of an alkyl halide, alkyl bromide, with a cyanide group. So to draw the mechanism of this one, we need to first draw the CBr group or the alkyl bromide group, and then put the different substituents. Attached to this carbon, there is a hydrogen, and there are 2 methyl groups. So now we can simply draw hydrogen here, and then 2 methyl groups attached to the same carbon. And then the nucleophile that's going to do the substitution is the cyano group here. Don't forget the lone pair of electrons. And the mechanism for the nucleophilic substitution reaction, the electrons from the lone pair of electron will move to attack the carbon, and then the bromide is going to leave. So this is the first part, which is the mechanism. And then they want the displayed formula of the amine G. So step 2, we have the cyano compound and we have hydrogen, which is hydrogenation reaction, meaning the cyano group will be reduced to give you an amine. So let's start by drawing the nitrogen. The nitrogen will have two hydrogens attached to it. And then let's draw the carbon of the cyano group here, this carbon, which is going to be reduced and two hydrogens will be added. And then the rest of the molecule, which is this carbon here. So now drawing this carbon, attached to it, there is a hydrogen, and then there are two methyl groups. So they want the displayed formula. So let's draw the two methyl groups in the displayed formula like this. So this is the displayed formula of your product. Finally, they give you two amines, amine B and amine Q. Amine B is P is a secondary amine with two methyl groups attached to the nitrogen, while amine Q has only one methyl group attached to the nitrogen. And they ask you to explain why P is a stronger base than Q. Of course, the basicity of the amine is related to the availability of the lone pair of electrons on the nitrogens and how fast they can accept a proton. So you can notice that amine B has two methyl groups, and the two methyl groups have a positive inductive effect or electron releasing property, which means that they increase the availability of the lone pair of electrons on the nitrogen. This is in comparison to amine Q, which has only one methyl group or one alkyl group. So the effect of the positive inductive effect will be less. So the answer can be that the lone pair of electrons, so the lone pair of electrons on the nitrogen, for compound P is more available due to the presence of two alkyl groups or attachment of two alkyl groups compared to Q, which has only one. And the alkyl groups have positive inductive effect or electron releasing properties. Alkyl groups have positive inductive effect, while compound or amine Q has only one alkyl. Electrophilic substitution reaction for the benzene ring is one of the most common questions in paper 2, AQA A Level chemistry. You will always find a question related to this reaction, and they will always ask you about the mechanism of the reaction. This is the question from the 2024 exam paper, and because this was about nitration this year, probably you're gonna end up with Friedel-Crafts acylation. However, you also may encounter this question in your mock exams. So in this question, they give you a two-step mechanism for the synthesis of an aromatic amine, which is shown here, two steps. The first step is the nitration step. The second step is the reduction step for the nitro into the amino group. So the first question, they ask you to state the two reagents needed for step 1. Step 1 is the nitration step, and in the nitration, to form the electrophile, we need to use sulfuric acid and nitric acid. So H2SO4 and the nitric acid. So these are the two reagents. And then they ask you to give the equation that allows the formation of the reactive intermediate. So the reactive intermediate is the NO2 plus, which is the electrophile. So here the easiest mechanism or equation you could write is the HNO3 plus H2SO4. That will give you NO2 plus, which is the electrophilic reactive intermediate, plus water molecule plus HSO4 minus. Then the third question is that ask you to outline the mechanism of the step one. This reaction has a very common mechanism. You should master this mechanism. So let's start by writing the starting material here. So this is the benzene with the two methyl groups, and then we have the electrophile that is going to attack here. This is the NO2 plus, and then the reaction starts by the curly arrow coming from the ring of the electrons inside the aromatic ring towards the nitrogen, which has a positive charge, and that will give you the first intermediate. And don't forget that you need to write the ring open with a plus charge inside, and then you add the NO2, and don't forget the hydrogen as well, and also don't forget the two methyl groups in the correct position. And then the following step is the when the hydrogen leaves as a proton and the electrons go back inside the ring to reestablish the aromatic system. So the final product will be the nitro substituted compound. Don't forget to put all the substituents in their correct position. And of course, the hydrogen plus will leave, or the proton is going to leave as well. And then the next question, they ask you to state the reagents needed for step two. So in step two here, there is a reduction of aromatic nitro to aromatic amino group. And in order to do that, we need to use 10 and HCl. So it's N and HCl. Normally in this reaction, when you use the 10 and the HCl, that will give you not only the reduced product, but also will give you the ammonium salt. So you can then use sodium hydroxide to get the amine. However, if you write the sodium hydroxide, don't just write it next to the 10 and HCl, because this is wrong. You have to say then sodium hydroxide, then add sodium hydroxide. Or you can ignore this completely and you will not be penalized. The final question is to state a possible use for the amine formed in step two. There are several uses for the amines. One of them is to be used as dyes. So you just need to memorize one of the uses of these amines. Let's answer this question from paper 2, AQA A Level Chemistry past paper exam. So this is the last question in this paper, and this question is about enthalpy of combustion. This is about the calorimetry experiment. And this question, they give you the diagram where limonene was burned using the calorimetry experiment in order to determine the enthalpy of combustion of limonene. The information they give us in this question is the mass of limonene that was burned, and this is 1.31 gram of limonene. And also they give you the mass of water used, which is 60 gram of water, and the delta T, or the increase in the temperature, which was 52.1 degrees Celsius. And of course, they always will give you the specific heat capacity of water, which is 4.18 joule per Kelvin per gram. And they want you to calculate the value of the enthalpy of combustion in kilojoule per mole for limonene. And they give you the molecular formula of limonene, which we're going to use it to calculate the number of moles, because we're going to calculate the mass. We have the mass, and we're going to calculate the molecular weight of limonene. First, we need to calculate Q, and Q equals mc delta T. M here is the mass of water, which is the 60 gram, and this is times the specific heat capacity of water, so this is times 4.18, and times the delta T, the change in the temperature, which is the 52.1. The value of K is 13066.68 joule. So this is the value of Q. And then we know that delta H will equal the Q over the number of moles. So we need first to calculate the number of moles of limonene. The number of moles of limonene will equal the mass over the MR. We're going to use the molecular formula of limonene to calculate the molecular mass of limonene, which is 136. So this is 136. So the number of moles will equal the mass of limonene that was burned, which is 1.31 gram over 136. So the number of moles is 0.00963 moles. And finally, let's calculate the delta H, which equals Q over N. Let's first use the value of Q as joules and find the value in joule per mole. And then we need to change that into kilojoule per mole and put the sign, which is going to be a negative sign because this is an exothermic reaction. So Q is 130. 66.68 over the number of moles, 0.00963. That will give us the value of 1356541 joule per mole. Now we need to find the enthalpy of combustion in kilojoule per mole. So you have to divide this value by 1,000. So it's going to be 1,356.541 kilojoule per mole. And don't forget that you have to add the sign as a negative sign because this is an exothermic reaction. So the final value is can be just say it's minus 1,360 if you're gonna use it as a three significant figures. 1,360 if you're gonna use it as with three significant figures. Then the final question in this paper, they give you a table, and the table shows the standard enthalpy of combustion of obtained for a liquid hydrocarbon without naming that liquid hydrocarbon. And this is the value minus 4194, and the value calculated from a calorimetry experiment, which is minus 1100. You can find that it's much less than the standard enthalpy of combustion. And then the value calculated using the mean bond enthalpy, again, it's different from the standard enthalpy of combustion, so minus 3159. And they ask you here, this is a 5 marks question, they ask you to suggest reasons for the differences between the values obtained by each of method 2 and 3 and the value obtained by method 1 in table 3. So if it's 5 marks question, then they need a minimum of 5 different points that you need to mention, even though you have more than 5 points you could mention, but the minimum points you need to mention are 5 points. So first of all, you need to state that the value of the enthalpy of the calorimetry or the enthalpy of combustion of calorimetry is less than calorimetry is less than or less exothermic than the standard enthalpy. And then you need to explain why. There are several reasons why the calorimetry experiment usually gets you a less exothermic value. The main reasons are because of for calorimetry, which is method 2, there is heat loss. Heat is lost or there is energy loss during the experiment. Also, there is a possibility of incomplete combustion in addition to the complete combustion. And we know that incomplete combustion will get you less energy than the complete combustion. Incomplete combustion as well is one of the reasons. And also the third reason for the calorimetry, why it gives you lower value, is because some of the hydrocarbon could evaporate or may evaporate. So if we lose some of the hydrocarbon due to evaporation, that means the value you get is actually less than the actual value. And then you also need, so far we have mentioned four different things, and now we need at least one more thing. So let's comment on the value calculated using the mean bond enthalpies. So the mean bond enthalpies values use enthalpies taken across a range of compounds, as we know. It's not the actual bond enthalpies for that specific compound. So you can simply say that the mean bond enthalpy method uses enthalpy taken from or taken across or from a range of compounds. So it's not the actual one. This is why it's less accurate than the standard enthalpy of combustion. So these are 5 points that you need to mention in order to get all the 5 marks. You could also refer to the fact that the value from the bond enthalpy data ignores energy changes in vaporization of the fuel or the condensation of water. This is why it doesn't account for all the energy that has been used during this experiment. So this is how to get the full marks on this question.